Okay, today, here's what we're going to do. We're going to do a little bit of MATLAB programming. The objective will be to take some data. We're going to make up a little data function. And, you know, the nice thing about data, drawing it, it's a lot easier to draw than actually, like, make up an artificial one. So you have some function of time, or you have to have someone who has real data to give you, right? But even like something like a music file is actually huge, right? Isn't it? I think if you actually take the data from that, it can be it's a lot, right? So you could get all the time resolution and so forth. So we're going to just take some of this data, and we're going to do a couple things. The morning lecture today, what we're going to do is we're going to build our own little Gabor wavelet, Gabor transform. We're going to put this on here. You know, rock that back and forth. Look at time and frequency. Okay? So mostly the idea here is to try to construct this time frequency picture we've been talking about all of last week. Okay? We'll talk a little bit then also the connection of wavelets, because all we're going to do now is take this thing, widen it, and shorten it. Okay? So that's basically a wavelet. So we'll look at how that changes what the time frequency idea looks like as well. Okay? So we'll do that. This afternoon's lecture at 4, I will then show you what you have available to you on MATLAB. Okay? Professional grade time frequency analysis tools. And in fact, there's a bunch of toolboxes. There is the wavelet toolbox. There is the signal processing toolbox. There is the filter design toolbox. Okay? All these things kind of doing all the same thing, but you got to pay 3 prices. Okay? But if you have the student version, it's like $29 each or something like that. Just a little FYI for you. Hopefully, many of you have it through your departments. Mostly what I'm going to do is show you the kind of things that they have in them. We won't be using them so much in class for homeworks, partly because it's too much to expect that everybody's going to have access to these toolboxes. Also, the homework 3 will be up this afternoon. And homework 3 is going to be something that you're going to basically construct your own little wavelet things, start looking very carefully at some data signals, do some time signal processing yourself. Okay, and I'll probably have you do that also in 2-dimensional data, and so you can start looking at stuff like that. All right, so that's the idea for today, right there. Sliding filters, time frequency analysis. Everybody good with that? Okay, so let's turn on the projector. I never know how long I'm going to talk here, so I don't like to turn that on because it leaves a, you need one of those buttons that you can say, shuts the projector without turning it off.
Here's a picture view on a remote control.
Yeah.
I have to show you the...
Oh, so is it on there?
It's on a remote control for that. Yeah.
Oh, okay. So that's, I got to learn how to work that.
I just discovered it.
Okay, and check it out. Will, we were talking, one of my students, he takes the Edge lectures and he takes them from a WAV file and makes them an MP4, and you can watch them on iPod. Does that sound awesome? He called it the 582 on the go. That would be awesome, right? And he was playing it on the plane, and everybody was over there looking, man, what you got playing on there? Is that the coolest movie ever? It's like, the stars on the plane. Anyway, I'm just saying, Will, just an idea.
No, we got the guy, he's done a couple of MP4 iPod stuff.
Yeah, there we go. Yeah. All right, but I'm worth it.
Yeah, I'll let him know.
I'm sure you can convince him.
Yeah, I can.
All right. So here we are, our beautiful MATLAB program, and we're going to make some cool stuff happen today. Woo! All right. Are you pumped up, Kristen, back there? You got breakfast champions. You should be yelling louder than everybody because you got breakfast. All right. So first of all, here's what we're going to do. Start off with our very simple, nice, clear all, close all, clear the screen command. So we start with a fresh slate every time we run this thing. And now what I'm going to do is take a domain. Let's start off with something here. Domain size is going to be 10. I'm just going to take a box size 10. Now this could represent 10 seconds, 10 hours, 10 microseconds, right? So whatever the units you are working with, that's your time frame that you've got. You've got a signal of a certain duration. 10, and I'm going to have I'm going to break this up because I'm going to use some FFTs into 2,048 points. Now, typically this number is given by experiments. These are your number of measurements. In time, if I've got 10 seconds, I'm sampling every millisecond. That's going to determine what that number is. But right now, we're just making up data. Fine. And then I make up some crazy function. So, first of all, I define a linear space. It goes from 0 to L, n plus 1 points. And I'm interested in the first 1 through n. So it's going to be, since I'm using Fourier transforms right now, I think about this being periodic. Essentially, when you use the FFTs, you are assuming periodicity. So I'll make the time domain be the first 1 through n points, standard. And I define some function. There's a 3 sine, 2t, a tangent, shifted over by a hyperbolic tangent, shifted over by 3, an exponent, Gaussian, another sine, a cosine with an argument squared. Okay, stuff like this. Now, let's just see what this looks like. You've already seen this function because I just recycled it from my notes from Wednesday lecture, I think. Okay, so let's just plot t versus s. Okay. All right, so it's not even that crazy looking of a signal. All right, but there it is. And the important thing that this illustrates, first of all, here's the kind of gross features you can see in this signal. There is some kind of long scale stuff going on. So low frequencies are involved, right? That happen over this 10 seconds. That's kind of clear to see. There's this sort of wave that goes through there. There's clearly over here some kind of, there's lack of high frequencies. Yet over here, very high frequencies here, high frequencies again here, not much going on here except low frequency stuff. So it's because we've made up some kind of crazy function. Most of the time what you get is you get a noisy signal. So there's noise on top of this too. Now we don't necessarily need noise on top of this right now. We can, but we'll just start off this right now. Okay? And we want to analyze the time frequency domain of this signal. By the way, there is a very good chance you've already seen time frequency analysis. You just didn't perhaps recognize it as such. Okay? Who loves whales? Now, if you don't raise your hand, you're a terrible person.
Regular whales, lake whales.
Well, both. I mean, we all love lake whales. I mean, that goes without question. Wow. PETA is going to have a field day with you guys because, like, nobody raised their hand about whales. I'm going to call them up after this class. You guys are all going to counseling. I'm sure the PETA people will pay for it, too. So you can love whales. The reason I bring up whales is because, well, not quite whales yet. Here, let's look at this. You see this figure I brought up here on the screen? This is a whale doing its whale. It's a killer whale talking. He's saying, he's wrapping up some Dr. Dre right here. And this is what it looks like. Some 3 different things he's saying. Like, this is where it's nothing but a G thing, baby. Right there. Okay, no? I don't know what he's saying here. This is a different part of the song. But that's how it comes out, looking in whalish. Here's time. Here's frequency. This is a time frequency analysis. This is what people plot when you want to analyze speech signal patterns. Okay? You don't look at this little thing that just looks all squiggly. You put it on here and you start seeing what frequencies are involved, when the sounds are coming out, how does it play out. So you've probably seen these. Have you seen any of these before? You know, they always talk, I don't know, I just generically, whale make music and they have whale CDs and you've probably accidentally seen a spectrogram. This is a spectrogram. You can send one to your loved one. Spectrogram. It's like a singing spectrogram. Okay. Everybody go with that? Here's another one. This is of a male human saying, ta, ta, ta. I pulled it off the web. There you go. There you go. Frequency time. There's your spectrogram. Okay, so if you're in speech recognition, this is the kind of stuff you look at all day. Okay? When someone says a t, 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 has a certain signature in the time frequency domain, so what you do? Well, you build something that recognizes that spectral time pattern, converts it to t. Right? So you can do the whole alphabet. You can do all these kind of words. This is how you sift through things and you make speech recognition. Okay? Speech recognition doesn't just take a bunch of sound waves and say, oh, that's the... You put it on here, you start doing statistical decision and processing of these signals, and that's what converts it over to trying to say, oh, that, I think, you know, when you do speech recognition, it types up on your keyboard. I have a very simple speech recognition right on my iPhone. I push this button, I say, I'll see you at 10 o'clock, meet me at the hub. Boom, pops up, and then I can send it as an email or a text, right? So even in speech recognition is quite advanced, and all it's looking for is these kind of spectrogram patterns of speech, okay? Many of them actually learn what's specific to you. I suppose if you're from the South, you might have a twang, and so it might have a different pattern that you would want to be generating here, okay? Or Jersey. Erica, you don't even have any Jersey accent, you know? No, do you need a cup of water? Do you need some water? So that would be like water and water, or, you know, they probably have two different signatures. All right, so this is what we want to build. How do you build this? You throw a Gabor window on this thing, you translate it in time, pull out frequencies, plot it. That's it. That's what you're doing. Okay? So all the stuff we talked about in lecture Wednesday is just, that's it right there. So we're going to build this ourselves right now with that signal I just created. Oop. Okay, so let's bring this back up. All right, do you feel motivated? Do you see how I brought that in about whales and saving them? That's awesome. All right. I should have worn a Greenpeace tie, and then you guys would be all like, whoa, and today we saved whales in class. That's right, because we can know how they talk. All right, plot T and S. We did. Let's go back to what we had. There it is. Now what's important about this signal is that different parts have very different behaviors. Here, in this region, high frequencies, low frequencies, high frequencies, and then there's some kind of overall low frequency pattern in the whole thing. Let's look at the Fourier transform of this thing. Okay, first off, that's the one thing that we know how to do is Fourier transform things, right? We almost are a little too casual. You can Fourier transform anything, and you get spectrum, and you just kind of say, oh, look at that. There it is. Here's all the frequency components. So first, let's define our frequency domain, 2 pi over L times 0 to n over 2 minus 1 minus n over 2 negative 1. Okay, there's our k values. So those are our frequency components for the FFT. And let's shift them. Let's call it KS as a shifted version because what we want to plot it against. FFT shift of K. So now what we can do is take this signal. We can say, all right, Fourier transform of the signal, ST, is just FFT of S. And now what I can do, let's start doing some subplots here. So figure 2 is going to be a plot of KS, the frequency components, versus, you guys probably can't see that, so let me bring that up a little. Is that better? Yeah, a little higher up on the screen? Okay. Frequency components versus the Fourier transform, which we have to take the FFT shift of this thing. Sorry, that wasn't even on purpose, although that's pretty awesome that I messed up. There we go, FFT shift, that absolute value. That's going to give us the Fourier components of this thing. So now let's look here. What? Oh, I needed something to shift. Okay, there we go. All right, there we go. Take that signal. There's its Fourier decomposition. Now let's zoom in a little bit here. I have a lot of Fourier modes, and all of it's concentrated down here. So that's a little bit better picture of it. And by the way, you'll probably recognize that from the notes, that picture there. I actually have that in the notes. So you can see this is made up, that signal is made up of a lot of actually Fourier components. Okay, in fact, but nothing beyond about k equals 50. This is like cosine 50x or something like that, but nice set of components there. You see some interesting features like 2 large peaks here, okay, at low frequency, and this would be this thing that's sitting underneath the whole thing. So you see a lot of the stuff here. And in fact, this is a complete characterization of all frequency components in that signal I showed you. But as we talked about, the whole reason you do time frequency analysis is because this thing here, yes, I have some frequencies like that, but I have no idea where it happens in time on the signal. If this thing is 10 seconds, what I do care about is, hey, I'm looking at this high frequency spike right here, for instance. Suppose that's of interest to me. I have no idea where that happened in the 10-second audio. Okay, so the Fourier transform gives you all spectral information at the price of sacrificing all time information. Okay? So let's start working then with the Gabor transform, because that's what we are trying to do here now. Is say, okay, what am I going to do with this Gabor transform? What I want to do now is I want to basically filter this in time, take little sections of it. So let's define like a little Gaussian as the simplest Gabor we could start with. G is the Gabor. I think it's a little g in the notes, so let's start with that. It's just a Gaussian. And first let's plot what this thing might look like, its width and so forth. So it's t minus 5. Let's center it on this signal S. And we're only going to plot the first plot here. And here's what we're going to do. Figure 1 is going to be a subplot of t of S. And that's going to be our signal in black. And then we're going to put this filter on it, this t of g, in red. And the new signal is basically SG, let's call it that, for the signal with the Gabor on it, is going to be G times S. Okay, so I just multiply my signal by this Gabor Gaussian, and I get a new signal. And then we're going to plot that in subplot. So I got to put 3, 1, 1, 3, 1, 2. Well, here we're going to plot T versus SG. All right, so now what this SG is, this is my Gabor signal. I don't know if you can get Gabored, but we just Gabored it. So here it is. You take the signal and you multiply it by that window. You get to pick the width of the window. You get to pick where it lives. And the whole idea behind the Gabor is to take this window, slide it back and forth. Okay? If I multiply these two together, this is the little piece of the wave that I pull out around time equals 5. Okay? So in some sense, I can think about, look, at time equals 5, I can pull this out. And now what I want to do is look at the Fourier components in this part of the signal. Okay? This is the way we're going to construct the spectrogram, because right now I can say, okay, at time 5, the Fourier components are, well, let's do it. Let's take the Fourier transform now of what's in that little Gabor window, which is SGT. Done. Fourier transform that. Let's make that subplot 3, 1, 3. Plot. Now what I'm going to plot here is Ks versus the absolute value of FFT shift of SGT. Okay, I think that's right. And go. And let's close up the Fourier domain a bit here. So on this one, I'm going to say axis. There was nothing really outside of negative 50 to 50. So let's say negative 50 to 50. And let's normalize it so I can always have it between 1 and 1 divided by the absolute value of SGT. Oh, max. So I'm going to normalize the height of this thing. So between 0 and 1. All right. There we go. All right, so now we're getting the idea of this thing. This making sense to people? I take my signal. I take a small portion of the signal by choosing where to place my red filter in time. Okay, so it's like the filtering process we learned about, which is, and you saved your dog with it, right? Okay. If you saved your dog, what you did is you did a filter in frequency. Now what we're doing with Gabor is a filter in time to pull out a small portion of the signal. There it is. And look at its Fourier components. There they are. This is one window of time. This corresponds to one slice of my spectrogram. Does that make sense? This is going to be at time 5. Okay, let me draw. I like drawing. Here we go. Ready? Here's what we're going to try to construct today with a code. This is the idea of the spectrogram, time and frequency. Right now, what I just did is I filtered at time 5, and I have the frequency components in that window. So now what I can do is say, okay, great. Now let's filter at a different time, and let's construct these frequency components, put it on a 3D grid, and I have my first spectrogram. It's beautiful. Okay, everybody go with that? That's what we're heading for? That's the big goal? All right, I can see you're all on board. It's great. All right, yeah.
Like wavelengths are going to
Yes.
narrow and widen it.
Yeah.
So not only do we have to do each different time position, but at each time position, we're going to have to do a couple different.
We'll do a little bit of that today in class. I'm going to mostly have you do that in your homework. So, but yeah, exactly it. So you have 2 degrees of freedom here. How well do you want to resolve across time? And with what width do you want to do this with, right? And the problem with the Gabor is right away, you can see the problem with the Gabor is that once you pick this red, there's no way that this red, for instance, it picks out just a small time piece of the window. The one thing that you throw away is all this long scale stuff because your window says it doesn't exist. By the way, that tells you the same thing. Remember those 2 big spikes right around -2 and 2? Actually, they're a little bit closer in. Those get kind of washed out because the very low frequency stuff lives outside of that window, and your Fourier transform doesn't handle it because you killed it off. Okay, so we're going to make a little movie. You ready? This class is exciting today, right? Who would have thought you'd come watch movies in class? Like last quarter, we always hear movies downstairs. Today, we got movies. No soundtrack. Don't worry. Maybe I'll play some whale songs for you later. But right now, we're going to watch a movie, a silent film, in color. All right. First, we have to build it, right? All right, so here's what we're going to build. We're going to make our MATLAB do the following. We're going to take this and actively put this in a cycle and just take our red and slide it. And as we slide it, we're going to watch what this thing is and what this thing is and how they evolve. And then we'll construct a 3D plot of those things. Okay? All right. Who's super excited at this point? Sweet. 3 people. 4. Woo! That's awesome. I was only expecting 1. Whew. I am on a roll today. All right, so here we go. Ready? Figure 1, we're going to loop this. Hey, you know, Dr. Dre does a Dr. Pepper commercial recently, and he's always talking about looping it because he's got a little thing, and we're looping it too. So it's awesome. I'm just trying to make those connections for you, just in case you weren't seeing them. All right, so let's do the following. Here is the big thing. The Gabor window is what we want to slide. So let's bring this into our loop. All right. And we're not going to slide it anymore by 5. This is going to be a variable. So let's make a vector of how we want to slide this thing. So let's do tslide. That's our sliding time. It's going to first start at 0. And we're going to slide it. We have to go all the way to 10. And steps up, I don't know, 0.2. Slide it, boom, boom, boom. Maybe that's too. Well, anyway, you'll see a cool movie with lots of frames. Okay, maybe that's too many. Let's do 5, 0.5. 0, 0.5, 1, 1.5. This is where this thing is going to be centered. And so I'm going to go do this for 1 to the length of tslide. What I'm going to do is tslide j. So every time I come in here, I better put an end statement here. So this is the way this is going to work. You've decided what kind of increments in time you want to slide by. These increments in time, by the way, depend very strongly on how narrow your window is or how broad it is. Okay? We'll talk about that in a second. But we've decided to slide it from 0 to 10 and half scale. You know, so there's going to be a total of 21 slides. And what we do with that is we say, okay, slide it. So I take my Gaussian centered around that point. I multiply it by my original signal. Fourier transform it. Now I plot everything. And what we're going to do is draw it now. And then it's going to come back through, do the next one, do the next one. So you just actively see this red thing just slide through this thing. And it's great. It's going to be so awesome. All right. Okay. Here we go. So the draw now command is a nice one because it tells it to not wait to draw it. So sometimes, by the way, why do I do that? You kind of would think, oh, it's obvious. It's going to do this, plot it, and then go to the next step. No. Sometimes when I was doing a lot of crunching in a TED, MATLAB will say, yeah, you want stuff plotted, but wait, I'm still doing this. So put a little figure box up there, and we'll never plot it until everything else is done. The draw now says, no, no, no. Plot it now. You are master. MATLAB gives you a hard time. Who's the master? You guys got to learn the answer. You say, I am. Okay. Who's the master? Oh, thank you very much. Good. That's good. This is good. By week 10, you guys are going to know. You're going to be talking to your computer. You're probably a little shy to talk to your computer this way, but come on. You're the master. So you tell this guy when you want to plot, how you want to plot, with what kind of lines you want to plot. You dominate. And that's how we're dominating right now. We're doing a draw now. And we can even say pause on that plot for a tenth of a second, or let's do two-tenths of a second. Okay, so it's going to plot it, see it, move it, move it, move it. So let's see if we did this right. We should see a sweet little movie here. There it is. Look at that thing walking across. Whoa. Dang, wasn't that the coolest thing you ever saw in your whole life? Okay. Okay, maybe not your whole life, but pretty close. Now we can do point 1, and let's just have it pause just a little bit longer because that was in fast motion. Okay, there it is. There's my Gabor window sliding across. Here's the little signal pieces it takes out. Look what the Fourier, how time and frequency are changing. So there we go. We should lock that in because that's so amateur looking when it has to rescale as we go across. But that's giving you all this time frequency information, and this is exactly what windowed Fourier transforms do. And this is the heart of analyzing your data in time frequency domain. Okay? Essentially what we just did here, this plot right here, was looking at these little sections, right? So we were looking at like making a movie of this slice, this slice, this slice, this slice. So now what we want to do, bring it all together with your hands. No, okay. Anyway, you bring it together and you make 3D plot P color from the top, and then we'll have our spectrogram. Okay? Everybody go with that? Was that kind of nice, right? Time frequency, it tells you all the frequency components, and then we'll start playing around a little bit with widths and so forth. By the way, one thing to notice right away. Let me show you something very important that's happening here. Oh. You see this thing sliding across? When I slide, I do a lot of oversampling. I slide just a little bit, so all the frequency components from this window are still mostly in the next window, right? Time and frequency are very closely matched. I have very good resolution. If I do a lot of oversampling like this, in other words, my filter moves very slowly across, this gives me a very accurate representation of time frequency. In other words, I choose how I want to slide my filter. If I did my filter here, one here, I can undersample as well, which is I miss this whole region in between, right? We'll do that in a minute as well. So let's build some spectrograms, and we'll come to that. Okay, so we'll keep that plot going, and now what we want to do is so what we want to do now is every time we get this information, this SGT, which is the important thing, what we're going to do now is say, oh, by the way, okay, now this is going to be important. When we plotted this thing, we always normalized the frequency components and their strengths to 1. So now what we want to do is have an absolute scale of these frequency components, at least on the, if we're going to do a plot of the full spectrogram, right? You may have a very intense signal at time 1, which all weakens at time 2. So you have to make sure to see that time 1 is more intense than time 2, for instance. And so you've got to make sure you got to take out that scaling there. Because now you're going to look at all the frequency and all the time components on one graph. OK. So that's one thing. But this is the quantity of interest. OK? And what we can simply ask about SGT is the following. What is it? Size. SGT. It's a 1 by 2048 matrix, or vector, which we know, right? It's one row, 2048 columns, because we did our data in 2048 points. We Fourier Transform, it's still 2048 points. Well, we want to do those now, right? Every single one of these as a row of a big matrix. With how many rows? Well, the number of rows is determined by the number of slices I took. Okay? All right, so here's what we do. We make the let's call it SGT spec. That's for our spectrogram. Okay? And what this is we're going to start off, by the way, we're going to collect all this data. SGT spec. First of all, there's nothing in it. It's a spectrogram, it's empty. Now, when I first create my first SGT, I simply add that row to what I have. So it's what it was before. And in the next row, I want to add SGT. I think that's right. So I start with one row of data. SGT is empty to begin with. But if I have a row of data, what I'm going to do is every row I get, put it on the bottom of that. So I take SGT spec is what it was before. So as I start building it, all I do is say, take what I had before, return character, go to the next row, place the new row in there. Place the new row in there. Everybody go with that? So this thing here should have a total of, I've done this here now with what, 100, 101 slices. So this would be 101. It's a 101 rows by 2048 columns. That's my data. Everybody good with that? At least in this construction. All right. Provided I did that right. And by the way, let's save not SGT, but the FFT shift of SGT and its absolute value. Absolute value right here. Okay. So that's what we're going to save. Yeah, Jason.
SPT spec.
Oh, SPT? SGT would be good, yeah. Okay, thanks. All right, ready? Well, okay, so that's going to be that. And then at the end of the day, after we get all that information, we can just do a p-color on SGT spec. It's going to be a top view of our spectrogram. Let's see if we did it right. Now, by the way, we're going to have it whip through here very quickly. Oh, I got to do, oh, sorry. This is going to be figure 2. Okay. Figure 2. So here we go. We walk it across. We're starting to collect all our spectrogram data. Look how the frequency changes quite a bit. Different components, different times in the signal. Pulling everything out. And. Let's see if we, right? Okay. And I know why it's black. Don't worry. Here's why it's black. You want to know why? I got the answer for you. Okay, when you do p-color, what it generically does is it draws, okay, I've cut it up into 2048 points this way, and there's 2048 lines. And there's 101 this way. Now, if you try to fit 2048 black lines on that much space, what do you get? A big thing of black. Okay, so what we need to do is shading interpret. Shading interp will take out the lines, smooth everything over. All right, so what we do is shading interp. So let's do this. Except for it's this is time and that's frequency, so we just need to rotate it. It's still looking kind of cool so far, right? Everybody cool with this? Yeah? All right, so now what we do is we look perhaps at its, let's try that. Oh, shoot, I didn't need to run it again, sorry. Anyway, you can never get tired of seeing this again, though. I mean, seriously, this is the sweetest thing you've ever saw today. You guys should just go home, call it a day. Why even go to your other classes? You know you're only going to go downhill from here. There is your first homemade spectrogram. Give it up for yourselves. No? Okay. Anyway, let's also work on the axis and some cool colors. Maybe you're not ready to quite give it up yet. After we do this, we do some axis settings on this. Maybe you'll be okay with that. You'll be comfortable with that. So here we go. What we want to do is set GCA, the y limits to negative 50 to 50. And then let's do color map hot. All right. Oh, well. Did I mess up here? Yeah. I mean, I didn't mess it up. I was just seeing if you guys saw where I've made a typo. Matt, Edwin, you see anything? Come on, guys. Help me out. Bail me out. I'm in trouble here. Shh. Come on, dudes. Come through for me. All right. Anyway. I do want to just go from negative 50 to 50. Don't I just do the X slim? Yeah? What's going on with that? So if I take this out, okay, let's just go back to here real quick. We're all good with this, right? Okay, there's that. Oh, yeah, that's right. Okay, it's negative 50, but I haven't actually put on axes here. So here's what we want to do is actually put our time, which was t slide, right? This is a function of t slide. No, sorry, actually, yeah, we have t slide times, right? That's the times that we have actual data on. And the other direction is ks, okay? And then I can set GCA. Shouldn't have deleted it. As it was, what it was plotting, because I didn't put the XY coordinates here, it was just plotting, oh, there's 2,048 points this way, and there's 101 this way, so it just plots it as versus 101 versus 2,048. Yes?
Does T-sliding mesh grids, or is that?
No, it doesn't even have to be mesh gridded. Turns out that it knows that if you do it as a vector, oh, I'm sorry I didn't need to run it again. But again, like I said, nobody can get sick of this, right? All right, right. Keep going, keep going. We're going to do this again, though, with a narrower and a broader little window here in a minute. Dang. Bow to the power. Super sweet, huh? Look at that. You built your first spectrogram, and who wouldn't want to get that in the mail? Like, send that off, sign it, love. Erica, here's your task for today. You're going to take this, you're going to print it, you're going to sign it. Love, Erica. Dear Mom, I love you. Graduate school is fun. I'm learning all kinds of things. This is a whale song.
I want a copy of that.
Will, you got one. I'll put little hearts for you, buddy. Little gold stars. It's coming your way. Don't worry. They'll be delivered in a campus mail. Will, basement of low. All right, so there you go. This is what people look at. That's your total time frequency domain picture. Time frequency gives you all the intensity of the signal and at what time the signal occurred. Great. Perfect tool for analyzing. So now we could build a speech recognition. Suppose that crazy signal was somehow a P. I said P, and that's how it comes out. Well, then you say, oh, look at that. That's a characteristic for that. When I get that time spectral piece, I can kind of save that away somewhere, and I can now start to recognize it. By the way, that's where we're going next. After next week, we're going to end up in starting asking these questions of how would you recognize stuff like this? How would you make some statistical decisions based upon time frequency information you have? So that's where we're heading. We still have the whole linear algebra component to bring into our data analysis that we haven't even touched yet. And when we do, super powerful. You think we're powerful now? Just wait. All right. Let's play around with filters, time filters. Let's look at this picture as you have it here. Now let's get to the question of, for instance, let's make our filter sharper. Let's make it broader. Let's see the kind of things we see. All right, so there we go. So first thing maybe we could do is make this filter narrower. How's that? Does everybody like that idea? So let's put something like that. Is that right? We'll see. All right. Anyway, it's going to change filter. There it is. Oh, no, we made it broader. All right, so fine. We're going to do it broader first. That's why also I thought, that's broader, right? So now we're taking huge windows. We lose some time accuracy. Look at the spectral structure. But now it's going to be harder to localize signals. It changes our spectrogram. So what this is really telling us is we've lost, essentially, remember there's a Heisenberg uncertainty principle that goes on with Fourier transforms. The broader the window we have more accurate information on frequency content at the sacrifice of less accurate localization of where the signal is in time. Okay? So we can trust this more this way and less this way. Okay? That's what that says. Right, so that's what this thing looks like if you take a broader signal. So you've gained some frequency resolution, and I think these signatures are sharper here. Is that right? If you look, I think there was a bright spot here, but these were not as bright before. What are these? These are the low frequency components. This is what that shorter window is throwing away. Now, you want to see these go away? Who wants to see them go away? Yeah, well, anyway, we're going to see them go away because we're going to take a very narrow filter now in time. And the narrow filter now is not going to allow for long frequencies. It's going to throw them all out. So once you throw them out, it's like, well, okay, these should kind of disappear, or at least be attenuated a great deal, because you're going to have good time resolution, but poor frequency resolution. All right, so now let's go the other way. There we go, and go. Here we are. There's my little window, a much smaller window, pulling out smaller and smaller bits of the signal, and same process, and this is the kind of thing that you get to play with, essentially, when you do time frequency analysis. You have to figure out what the optimum is. Check this out. Quite a different picture. Excellent time localization. There is a big peak here. Do you remember how this looked before? Kind of washed out, bad time localization. Now we get very good time localization. We threw away a lot of frequency content in this process. Okay? So that's the trade-offs you make. Still looks pretty cool, right? We got holes in there. I didn't expect that, but there you are. You have little holes. Let's make it even narrower. Let's go here to 10. So you see, this is nice. It's getting very good resolution. The width of that thing is, less than a unit. It's about half a unit. You're pulling out quite a bit of information there. And so you can get the good localization in time. It's just that now you start losing a lot of the frequency aspects of the signal. Okay, this frequency just starts getting washed out. There are almost, remember those two big frequency components here? Completely lost. So if you go to these very short windows, you throw out any of the kind of low frequency components that might exist in your signal. Okay, and those might be very important for you, right? So it all depends. So you can always, but you can also build histograms or these spectrograms based upon, hey, I want to actually filter for low frequency content. Let's not worry about so much localization in time. Low frequency content is not localized in time. That's the point, right? It's long. Okay? And so you get things like this. All right, what else should we do with this thing? That is just one example. Let's do one more with a very broad window. Now this window here is pulling out almost half the signal, right? That thing here is half the time, about half the window. So you see that you got a lot of Fourier content, And when you look at this thing, look at the difference. Now, we could have plotted both side by side. When did this thing happen? Here. In this big window, you're going to go like, there was something happening here between time, I don't know, about 4 to 9. So you kind of know this 5-second window range that something would have happened in. Now, when you go to the time domain picture, right, this thing squeezed down to, you know, it happened at right around time 6. Right? So right now, you have, so it's good here. You get, look at that, good strong signatures of the Fourier components here that totally got washed out. All this middle region gets washed out essentially by the short window. So you get the good short window stuff here. And this is where the wavelets comes. Okay, so now, so the wavelet idea is to say, can't I kind of take advantage of both? Can I get good time and frequency by starting with a big window, getting these things out, now going to a shorter window, getting the next things out, getting the shorter window, so I can actually sort of localize this and localize this. That's what wavelets are trying to do for you. Okay? It's about 18 after. So, lecture 2 today, 4 o'clock, super awesome here. And I'm actually going to introduce you to some of the MATLAB toolboxes that do some of this for you. Okay? So I'll go through a little 3 toolboxes. We'll just walk through them a little bit. And then on Monday, we start image processing. Okay?